3.8 common ion effect. All right. So, what's the only thing that can change the KSP value? Temperature is the only thing that can change it. All right. Or solubility can only be altered by temperature. All right. So, but we're going to change the solubility by using common ions. All right. Which is what we did right at the end of that little review I gave you right there. Don't worry about this. That's sort of a math analogy that we don't need to worry about. Okay, if you have salt, table salt, NaCl, you throw it into a saturated solution, or you create a saturated solution. You get this equilibrium happening. Okay, it breaks apart into its two ions. Now, if you think back to the previous chapter when we did KEQ and whatnot, if you increase the concentrations of sodium or chlorine, what happens to the equilibrium? Which way does it go? It's going to shift back left, right? Because you've added a stress. Okay, so we shift left to counteract the shift. Because this is a solubility reaction, we're going to create a precipitate forming, right? Because this is a solid, right? So the NaCl will precipitate out and fall to the bottom. But you don't have to just add more salt to do this. You can add anything that has sodium in it. So if I add sodium nitrate, the nitrate is a spectator, it doesn't do anything. But I'm going to increase the concentration of sodium ions through this atom here, which will result in the same thing. This spikes, and the reaction is going to shift left. And you can dissolve less salt in a sodium nitrate solution than you can in pure water. Does that make sense? Because you already have that. You can also do it by spiking just the chlorine. So if you added, say, calcium chloride, you're going to spike the chlorine. That's going to push the reaction backwards. So less salt will dissolve in a calcium chloride solution as well than pure water. Okay, pure water is like the baseline. All right, and then if you add any common ions, it's going to be less than that. Okay, so any addition of a common ion will act to decrease the solubility of a compound. All right. So we're going to look at it qualitatively, just talk about it, and then we're going to do the quantitative reaction and look at the numbers behind this. So if we have, strontium sulfate in pure water, that's going to be our baseline. Okay, that's going to be the maximum amount that you can dissolve. This is the controller reference. This is the max amount you can dissolve. Relative, right? It's all temperature dependent and blah, 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 blah. But for this sort of three version experiment we're going to do, that's going to be the max. Then I go, okay, let's dissolve the strontium sulfate in 0.1 molar strontium nitrate. Okay. Well, if you're in, so you have a beaker, strontium nitrate. Have a beaker with strontium nitrate in it, right? The strontium nitrate dissociates. You get strontium ions. The nitrate ions are irrelevant for our reaction. Okay. I'm adding in, and then I want to add in strontium sulfate. So strontium sulfate enters the equation, or the beaker, I guess. And does, or wants to do this. It wants to dissociate. But in our beaker, we already have strontium ions. So what happens? Yeah, it's going to block it going this way, right? Because we already have a bunch of this in solution. So you add this in, it says, I'm already here, get out, and it pushes the reaction back that way. Does that make sense? Okay, so it's blocking the dissolving of it. So causing stress, equilibrium will shift left. Why is my... Come on. Left. Therefore, qualitatively, we would say strontium sulfate is less soluble in strontium nitrate. That's all we can say right now. We'll do the math in a sec. But we're just saying that it's less soluble because we already have strontium in our beaker. Are we good? Okay. Then we go, okay, what if we try to dissolve strontium sulfate in chromium sulfate? What's going to happen? It's going to block again because we have the SO4 2- ion in solution, right? Is already there. But what do you notice? It's 0.1 molar of this. How many sulfate atoms, or sorry, molecules are there in one of these chromium sulfates? 2. So the actual concentration of the sulfate is 0.2. It's higher, right? So is it going to be more or less soluble than the strontium nitrate? It's going to be less, right? Because this is 0.1 molar, but there's only one strontium here, right? And we'll, like I said, we'll do the math here in a sec. So this is 0.1 molar. But if we put 0.1 molar of this, and this dissolves according to this reaction, you have 2 of them. So if this is 0.1, that's 0.1. This is 2 times 0.1. So it's double the concentration. So you have even more of the sulfate that is like, no, I'm pushing back even harder. So less, it'll be even less soluble than strontium nitrate, or it should be anyway. Does that, I'm going to ask you a question like this on a test. Does that make sense? Right? You have more of it just because we have 2, I didn't even write that, right? We have 2 of those for every molecule. So if that's 0.1, you get double the amount. All right. Okay, that's the qualitative. That's what we think is going to happen. Let's do the math, because doing the math is always better. Right? So true. Okay. So qualitative or quantitative in pure water. This is the basic. This is what I've asked you before. What's the solubility, okay, of strontium sulfate in water? So we do our ice table thing. Initially, we have no strontium. We have no sulfate because we haven't added anything. We just have a beaker of water sitting there. Then we add the strontium sulfate into the solution. So I put in an X amount. That's going to give me X of the strontium, X of the sulfate. So at equilibrium, we have X and X. This is the stuff we've been doing, right? Okay, so the KSP expression is the concentration of SO4 2- times the concentration of strontium. KSP is right here, 3.4. And that'll be X squared. Everybody agree with that? So then you square root it, and you should get so 5.8 times 10 to the minus 4 molar is the solubility. That's how much strontium sulfate we can add to pure water before we start to, it saturates itself. Okay. So that's the max. Now we're going to take the same question and we're going to say, okay, we have a beaker of 0.1 molar strontium nitrate. And we're going to add strontium sulfate to that. Okay? We already have strontium in there from this, so it should be less. That's what the numbers should indicate. Okay? So when you set up your ice table, initially, how much strontium is in there? 0.1, right? Because that's what's in the beaker. There is no sulfate, and we don't care about the nitrate because nitrate's a spectator. Everybody agree with that? Okay, so the nitrate's useless. We have 0.1 molar of strontium. Then we add in the strontium sulfate. We add a certain amount. I don't know what it is. X. So then the change is plus X, I guess. Plus X. So at equilibrium, what's the strontium sulfate? Or the strontium, sorry. 0.1 plus X. And then that's just X. Is that okay? Yep.
Why are we leaving 2 o'clock?
Well, I'm just, this side is almost irrelevant because it's a solid. But I'm just saying initially in the beaker, I haven't added any of this yet, right? So I could put a 0 there if you want. 0? You like the completion? Okay. So 0. And then, but we do have strontium. That makes sense? Okay. Then we add a certain amount of X. That would be the change. So we get plus X plus X. And I guess here we should put, well, you can put X if you want, but it's, yeah, so it doesn't really matter. Okay, the KSP is the same because it's still strontium sulfate. So we go KSP is equal to concentration of strontium, concentration of sulfate. Okay. Why is this question different and more difficult than everything we've done before? You're going to form a quadratic equation. Now, slow down before you do anything and freak out. Okay? Okay, it's calm. Does everybody see you're going to form a quadratic here? Because what you're going to do, but don't do it right now. Don't do it. You would dump the X in, so you would get this. That's what you're going to generate. Okay? That is a quadratic equation. It kind of isn't a fun one because you got 3.4 times 10 to the minus 7 here. So unless you know two numbers that multiply to that and add to that off the top of your head, you got to use the quadratic formula. However, we are not mathematicians in this class. All right? As soon as you walk through the door, all the maths, we're not math people anymore. We're chemists. Okay? Chemists aren't using that. So chemists have a little trick. Okay? And it works. It's not just, you can do the math using the quadratic formula if you choose. It's more work. You can do it if you want. You get the same answer. But let's think about this for a sec here. This is the part that's messing us up. Do we agree with that? This little thing right here. This 0.1 messes everything up, right? Because that's why you generate this, which is a quadratic. You can't just solve that normally. So chemists go, okay, 0.1 plus X. You can just watch this. You don't have to write this down. What's the bigger number? 0.1 or X?
Are you just going to get rid of the 0.1?
I'm asking you, what is the bigger number? 0.1 or X?
0.1.
Are you just guessing?
Well, no, because it probably like the answer is always like 10 to negative something. Like that's what X usually equals, right?
Okay, so what would X, what's the max value X can be? This one, right? Does everybody agree with that? This is the max that x can be. Okay? Everything else has to be less than that. So, as a chemist, we say 0.1 is going to be much, much bigger than x. Okay? Therefore, ignore the x value. Okay? You can ignore the x value. And the reason you can do it is if you think about it, let's go like this. 0.1 plus the x. The maximum the x can be is this 5.4 times 10 to the minus 4. So if I actually write that out, it's like this, 0.00058. All right? If you add those together, you're going to get 0.10058. Sig Fig says I should have how many answers? How many digits? Should have 1. So what does that round to? 0.1, right? It doesn't matter. And if you use the quadratic formula, it works out the exact same. The sig figs are what make that irrelevant. Okay? So sig figs tells us it equals 0.1. Okay? So because the 0.1 is so much bigger than the x, and you're just adding them, we just say, don't worry about the x. Okay? Sig figs tells. I should say tells us. Tells us it's going to round to about 0.1 anyway. So who cares? But if you want to use the quadratic formula, be my guest. It actually works out. You'll get the same answer when you actually do the math. We're not done yet. So you don't have to do this step right here. Don't do that. What you do is off of this step, I'll rewrite it here. 3.4 times 10 to the minus 7 is equal to 0.1 plus x times x. Just say off to the side somewhere, you have to write this though. You can't just like make things disappear unless you say why you're making them disappear. Okay? So you're going to say x is much, much smaller than 0.1. Therefore, we can ignore. You don't have to say the ignore, but you can just say x is less than twice 0.1. So this equation becomes 0.1x. All right? That x is gone. So now it's super easy to do. Just divide off the 0.1. And if you divide off the 0.1, you'll get 3.4 times 10 to the minus 6. Does that line up with what we predicted? Is that number bigger or smaller than the maximum amount? It's smaller, right? Because the maximum amount is 5.8 times 10 to the minus 4. And we just showed that if you have strontium already in there, it drops to 3.4 times 10 to the minus 6. So a smaller amount. Less can be dissolved in the solution. Okay? So the trick here is if you ever get to a point where you've generated a quadratic equation in this class, you have missed an assumption somewhere. Trying to think. Don't have to use the quadratic equation in this class. Okay? So if you are, you're either doing it because you choose to do it. Don't do that. That's way more work. Go back and look to see if there's an assumption that you missed. Okay? All right. One more. Last one. What if we do the chromium? Should this number be higher or should be bigger or smaller than this number? It should be smaller, right? Because we're going to have double the amount of sulfate. All right. So, all right, we're gonna do the ice table on our own now.
Wait, Mr. Baldwin.
Yeah.
Do we lose marks if we forget to define a variable?
Yes.
No.
If you do it on every,
Like, how important is it really?
it technically it is important, and we should, and I haven't been doing it. Let X equal concentration SRS. Oh, did it? Oh, there it is, right there. Look, if you, I will be forgiving. How's that?
I actually don't even know what that means.
I don't know what it means either. Okay, so we got a beaker of 0.1 molar chromium sulfate. All right, we write our ice table for the solubility of strontium sulfate. So we know it does this. ICE. Okay.
Why is there two?
Sorry?
Why is there two on the sulfate?
That's the charge. No. So remember, we're dissolving. I'm writing this. This is what I'm doing.
Yeah, why is there a two? Why is strontium two?
Oh, why isn't there a 2? You mean that?
There's not supposed to be.
Yeah. Oh, I see what you're saying. That. There we go. I guess I should erase the brackets in too. There. Okay. Strontium sulfate. What is the initial concentration of the sulfate in the beaker? It's 0.2 because the strontium, this is already sitting in the beaker, right? And that dissociates according to this. That's chromium 4. And you're going to have 2 of those, and it's 0.1 molar, so it's 2 times 0.1, which is 0.2. Which means in our beaker, we have 0.2 molar sulfate sitting there already. And we have 0 of everything else, 0, 0. Okay. Then we add a bunch of strontium to it, strontium sulfate. So our change is, we can say, I'll put the X. I don't like putting them there. Can I put Na? No, I'll just put X. So I get X, X, equilibrium, X, X, 0.2 plus X. Okay. What's the KSP? (3.4 times 10 to the minus 7). So you get to that point. 3.4 times 10 to the minus 7 is equal to X times 0.2 plus X. Okay. Do we like the quadratic formula in this class?
Yeah.
Noah does. Nobody else does.
No idea what on the back.
So, what do we write?
Get rid of it.
Just get rid of it?
Yeah.
All X's?
Well, just the one we don't like. The one in the bracket.
There we go. 0.2 is much, much bigger than X. So then we can just go ignore that, and we get is 0.2x. Then we divide off to 0.2, and we get all right. So just a little table just so we can see them side by side. Okay, so you can see in pure water, that's the highest concentration you can have, which is 5.8. If we throw it into a solution that is 0.1 molar strontium nitrate, because strontium's already there, it pushes the equilibrium back, so we actually dissolve less. It's 3.4 times 10 to the minus 6. And if you put it in 0.1 molar chromium sulfate, because it's a 2-to-1 ratio, it stops it even more, and we get 1.7 times 10 to the minus 6 molar. That make sense? Common ions will decrease the concentration or the solubility of anything. They push the equilibrium back. That's it. KSP unit is over. Please finish the package. Finish package. Tomorrow is some sort of lab. I'll put post review packages as well tomorrow. Test is on Tuesday. On the whole, yes, it's on the whole unit.